All right, so we're happy to have Humberto Moreira giving the first of the two papers in this prize session. These are excellent papers. Humberto, you have 40 minutes, so take it away.
Okay, thank you very much, Henrique. Thank you for the organizers of the meeting. So this is a joint paper with Vitor Farinha, who is present here in the session, and Piero Gottardi from Access. And this paper is about risk classification in insurance market with two dimensions of heterogeneity, right? So what is the main motivation of this paper is to recognize that insurance market risk classification consists of the use of individual data in order to access or classify individual risks, and as a consequence to better fit or their premium offers, so to do a better match with the insurance providers. So if you think a little bit, this is very intuitive. The use of more information may reduce the information asymmetry on one hand, but on the other hand, it also introduces price dispersion, because now the price is going to depend on other information, and that can hurt the insuree since he is risk averse typically, right? So what you want to do in this paper is really to understand the welfare impact of risk classification in this sense, and in particular, under condition can we access when exactly this risk classification can be welfare enhancing, right? So in order to do that, we are going to introduce a very parsimonious model to study this kind of question, featuring perfect competition, as in the traditional Rothschild-Stiglitz model. So this means that firms act as price taker in the market, and we're going to do only two dimensions of heterogeneity, which we're going to argue that this is going to be key. You know, the fact that the asymmetric information is going to be two-dimensional is going to be key to provide some analysis in this respect, right? So if you come back to the classical Rothschild-Stiglitz, which is the departing point of this kind of analysis, what you're going to see there is that the equilibrium is going to be separating, right? So each risk type is going to get a different amount of insurance of coverage, and because of that, the equilibrium is going to be prior not dependent, right? So the prior distribution of the characteristics does not going to affect the equilibrium outcome. So if you go to alternative models as Dasgupta masking, Dubey-Janakoff, which is a generalization that introduced this kind of pooling equilibrium, but since we have one-dimensional, even the Guerrieri-Scheimer that I'm citing here, which is not exactly in insurance context, but in this kind of paper, like Guerrieri-Scheimer, you're going to have like a one-dimensional sufficient statistic to characterize the private information, which is common for the provider of insurance and the insuree, right? So what you're going to argue is that multidimensionality of the heterogeneity is very important in order to get that kind of dependence of the outcome to the distribution of characteristics, right? And so the channel that is going to be explored in this paper is that this kind of multidimensionality is going to allows us to the possibility of cross subsidies and distribution effects in the equilibrium, right? Which is not present in one-dimensional kind of model. And if you go to the empirical literature, although this is not an empirical paper, but you're going to see that there is a huge evidence, very recent, showing that multidimensionality is very important. So just to give an idea, this paper by Cohen and Einap, they provide a structural model to estimate risk preference from the data on deductibles choice in automobile contracts. And they show that an observable heterogeneity in risk aversion is greater than that on risk, and you're going to illustrate exactly this point, in our theoretical model. And if you go further in the empirical literature, you're going to see that the recent paper tries exactly to document this kind of importance in terms of the empirical analysis, right? So as
Can I ask a question? I don't know what's the protocol.
Yeah, go ahead, Bryce.
Okay. So because there is now the competitive search literature now, there are papers that deal with multidimensional heterogeneity. So
sure.
Guerriere and Scheimer have a paper. I think Brianna Shung has papers, and there's someone at NYU, Basil Williams, I think, also has papers. What is the relationship between what you're doing?
The Guerriere Scheimer, the Shung paper is very close related. So it's like they have like a continuous pooling, but she does not explore this kind of impact of the distribution on the equilibrium outcomes as we're going to do here, especially this risk classification or the signal disclosure history that we have here is not present in this kind of paper. Guerriere Scheimer paper is a multidimensional, but as I said, it relies on the idea that we can map, this multidimensional characteristic just one dimensional characteristic, and then you go back again to a kind of one-dimensional analysis. It's true that we can play with the distribution and see the impact, but that the effect is going to be mechanical. You don't really going to see how the distribution is going to affect the elasticity of demand for insurance in this kind of model, right? So it's true this model has a little relationship, but I think your model brings some features that are not present, especially the analysis we're going to do here in terms of what you call risk classification, right? That's our main difference. I don't know if Vito wants to, put more information on this answer, but I think this is pretty much the difference between our contribution and theirs.
No, so right, just to add something mentioned, both of these papers, Chang and Guerriere Scheimer's, the preferences of the informed side, they're such that at any two types, they're indifference curves either satisfy single crossing or they are identical. So this means you can find the one-dimensional,
sufficient statistic that
for the private information of agents as it comes to their preferences over context.
Exactly. In our case, you cannot do that, right? So what this paper does, so you consider, as I said, a price-taking competitive insurance model with risk dispersion and preference heterogeneity. That is these two dimensions that I talked about. So we provide equilibrium characterization, right? So our model is going to be parsimonious, in a way it's very simple, but although it's simple, it's very hard in general to do the equilibrium characterization in this kind of model. And the methodology you're going to use in this paper is also new. We study like a neighborhood of a model with a pure risk heterogeneity. What I'm going to do here, because of equilibrium multiplicity, there is going to be an issue in this kind of model as well. You're going to treat that multiplicity doing like an approximation to the one-dimensional model, which has a unique equilibrium. So you're going to see how, departing from one-dimensional model, how the introduction of a small heterogeneity in this risk preference dimension is going to introduce some, effect of the distribution on the outcome of the equilibrium, right? So this is going to leverage, for sure, the tractability of the one-dimensional model and highlights the novel qualitative results that you're going to have in this paper compared to the one-dimensional literature, right? So the novel effects, what are the main results you're going to get from this exercise? So first of all, yes?
I didn't quite understand. Are you saying that you're going to select one equilibrium by looking at a perturbation?
I'm gonna, to be more precise, I'm going to show that since I'm using this neighborhood, this small neighborhood of the one-dimensional equilibrium, you're gonna see that all the equilibria that I'm gonna have in the model are gonna have the same properties. It's gonna be robust in a way, right? For a very small departure from this one-dimensional model. It doesn't matter which selection you're gonna get, the qualitative results are gonna be the same if you play with a small neighborhood. That's the goal of the analysis, right? So in general, you have the multiplicity, and with the multiplicity, you cannot really pin down in general what is going to be the effect, right? The effect can be, ambiguous, but in this, if you departed from a small, neighborhood of the one-dimensional model, you can sharply say what is going to be the result, what's going to be the effect. Do you understand, Eduardo? All right.
Yes, I got it. Thanks.
So there are two kinds of exercises you're gonna do in this paper. One is the signal disclosure, which is exactly connect with this risk classification story that I was motivating first, right? So what you're gonna do is that you're gonna introduce a kind of monotonicity property, a kind of the definition of monotonicity of the signal structure. And with this monotonicity condition is by chance, by coincidence, or by luck, is really related to some measure of entropy divergence in the literature. So it's not that we are using the entropy as a way to measure the monotonicity, but the monotonicity property that we identify that leads to the welfare enhancing property is naturally related to this Kullback-Leibniz divergence measure. I'm going to explain this better when I present the result. So with that, we're going to really have like necessary and sufficient condition to show that when a signal structure is going to be beneficial for the insurer, right? So it's like a characterization result in terms of what are the signal structures that are going to be the ones that you want to release information, right? And in terms of the comparative statics, we're also gonna see that, if you think about the policy intervention that tries to change risk distribution in the market, we have a sharp answer when this risk change in the distribution is gonna be beneficial or not for the economy, right? So the key point here is to show that the way you measure the risk how you compare the risk distribution is key, right? If you use first stochastic dominance kind of definition, then that's not is not going to lead you to exactly always the signal is the higher distribution in terms of first order stochastic dominance is going to be worse for the insurers. But if you use a stronger notion of comparison like MLRP, then that's exactly the precise concept that leads to this comparison between risk distribution, right? Let me go to, so I'm going to skip that. It's just, the literature very briefly is just to say how our paper fits into this literature. So you have like theoretical models, 2x2 models, no single crossing models, and on the side of the multidimensionality, on the side of the competitive structure, we have like a huge literature. More recently, we have this paper by Azevedo and Gottlieb. They have like a general existence and result in a very general multidimensional model. Our model, is related to theirs, but you are more precise in terms of the characterization. They don't really have a characterization result in their paper, right? So they have like a more approximation plus a numerical way to access, but they don't talk about multiplicity. They don't really talk about this kind of risk classification signal disclosure that we have in this paper, right? On the empirical side, I just mentioned briefly that. So there are a lot of interaction between the empirical literature and the theoretical literature that is going to be very important. So we think that our paper can be also potentially important to do the empirical analysis. That's one thing we want really to sell from this project, right? So the model. So as I said, the model is very is very simple in a way. So an insurance contract is a pair of numbers, real numbers. One is the price, right, per unit of contract, and the other dimension is the coverage, which is going to be normalized between 0 and 1. So you can think as a share of coverage. And the consumer's preference on coverage is going to be a quadratic specification, right? In this quadratic specification, there are two parts. One is linear with respect to the coverage level, which means that the marginal willingness to pay for coverage is exactly his type, the risk type, which is mu. And there is a quadratic loss, which depends on the difference between x and 1, which is one is the maximum amount of coverage, right? So as you go, if you are most coverage, so the loss you feel is lower, in a quadratic way, and is weighted by the risk aversion parameter here, rho, right? Minus the price you pay per contract, right? So that's the utility of the agent. And these are the two dimensions, the risk level and the risk aversion, risk preference parameter. And you can formalize, or you can give a fundamental structure for this kind of preference if you think about the current normal formulation. So you may think as a guy having a loss, which is normal with mean mu and some variance, then, and the guy has a risk aversion utility, constant risk aversion utility with the rho parameter, then you're gonna have like exactly this specification of his preference. On the firm side has a cost, which is the amount of insurance times the risk level of the guy that is buying this amount of insurance, right? So I'm not considering administrative cost and any other kind of cost. It's very simple standard cost, linear cost, right? Any question about the model so far? Okay. So in terms of the characteristics, so first, the mu is going to be a continuous parameter between a mu L and mu H. So the low and the highest possible level of risk, which in the prior distribution is given by this phi function here, which is smooth, positive, strictly positive and smooth. And the risk aversion, which is the risk preference parameter here in this model, is going to be binary, right? So this is the simplification, right? So the mu is going to be continuous and the rho is going to be binary, right? So you're going to have a low risk aversion, a high risk aversion. And delta is going to be exactly the difference between these two levels, right? The high and the low risk aversion, right? So you can think as the dispersion of risk aversion between these two classes of risk types, right? So, for this presentation, you're going to assume those dimensions are independent, and we can easily generalize the results for the case when they are correlated, right? So, but for the simplicity of the formulas and disposition, let's consider the independence case, right? So, what is an equilibrium? It's a competitive equilibrium. So, an equilibrium is given by two key elements. One is the price function. The price is a function that maps every level of coverage into a real positive number, which is the price of that level of coverage. And instead of the usual traditional way to present the allocation, which is a map from types to allocation to the coverage level in this case, you're gonna, it's more convenient to talk about the type assignment object, which is map for each level of coverage, which are the types that are gonna be attached or assigned to this contract level, right? So this means that there are, since that we have just two levels of risk aversion, so we can see that the mu I of X is going to be all the type mu, such that the mu and the rho I, which is this I here, choose the coverage X for each possible level of risk aversion. So I'm kind of dividing naturally this space of types in these two, sets, which are the high and low risk aversion types, right? And I'm going to map each X to possibly this type. It's possible that one of these set is empty. So for a given level of contract, I was going to see there is just the high risk averse type or the low risk averse type associated to that level. Or you may have like a continuous pooling that's going to be an interval, or you may have like a discrete pooling. Exactly, given one level of risk of coverage, you're going to have exactly two types that are going to be choosing that level of contract, right? So that are generally the possibilities of allocation here. So the equilibrium definition is this triple: the price, the type assignment for each risk averse level. And this triple is going to be an equilibrium if it satisfies the price consistency, which comes from the firm's optimality, since there is a free entry, and the firms are risk neutral. So in equilibrium, the price should be the cost of X should be the X times the expected risk, given which types of risk has chosen that level of coverage, right? So this is exactly a zero profit condition on the firm sides. X, on the other hand, should be optimal for the insuries. It means that, in these terms of this language here, it means that the mu and the rho I should be, choosing the X level, right? So this mu I represent the choice right? The optimal choice, you know. And we also have a third condition, which talks about the off-equilibrium contracts. You may have some contracts that are not going to be traded in equilibrium, so you want to say how the price is going to be for this contract. The basic idea, I'm not going to present the detail because it's going to be a little bit longer. So it's the idea that this contracts are going to be priced for the type that has the most willingness to trade those contracts. That's the basic idea. And it's very related to the typical refinement we have in this kind of literature, right? So the equilibrium analysis. So the first thing is that, you know, first from the zero profit condition, you see that the price per unit of coverage is going to be exactly the expected risk, given the contract chosen by the types that are chosen this level. This is exactly the zero profit condition. And if you play with the first order condition of the issues problem, then you're going to see that the marginal price, the marginal cost per contract X, you know, at margin, should be the marginal benefit. The marginal benefit is mu, the risk, and this quadratic term, which is it's related to the quadratic loss in the utility function of the insurance. So you see that here you may have like potentially two types, you know, that you're going to have exactly the same marginal, paying the same marginal price. You know, if you play with this row here, you know, for low and high risk averse. So, you know, if you take the expected value, conditional expected value, so you're going to see, you know, you're going to see that the marginal price is going to be the expected risk times the expected risk aversion, which is exactly this formula here. So this is exactly the expected risk aversion given the X chosen, times 1 minus X, right? So if you plug in, you know, that formula into this one here, you can find the ODE, right? And, you know, arguing that the highest type is going to be covered completely. So means that the highest risk type here, which is mu age, is going to be choosing coverage 1. And now you can easily solve this ordinary differential equation here, right? But the problem is that we really don't know what is going to be this, you know, this average risk aversion here, right? This is an endogenous object. So this expected, you know, risk aversion is given by the weights of these guys in equilibrium, and these weights in equilibrium depends on the prior distribution and depends on the demand elasticity of the insurees. So this object, this formula is not complete, solvable, because you don't really know what is behind this row bar here, right?
All
but
right.
what is important?
What's the definition of row bar? I missed that.
This is exactly that. So this is the average risk aversion. Right? Okay. So if you take this formula here and take the expectation in both sides, you're going to get this expression here, and you plug in this, you know, zero profit condition here, and you're going to get this ordinary differential equation here, right? Mm-hmm. So if you see like this, you know, oh, you solve the model, there is no problem here. Oh, it's not true because you don't really know this row bar. You have to really pin down this row bar. That's the complication of the model, right? So, for instance, in one-dimensional case that I'm going to present in a minute, then it's over because this is none, right? This is going to be a rho naught, which is the level of risk aversion that is known by the population. But here is an average of something that you don't know the realization. You have to come up what is the weights of this this type rho in equilibrium, which is endogenous, right? All right. But what this formula is important, and I want to highlight that, is this top-down effect, right? Now, if you see a type that is choosing a given level X, so it's what is important for him is not only, you know, his risk, right, but all risk that is coming above him, all the types that are choosing higher level of coverage, right? This is actually given by this formula. This comes from incentive compatibility constraint. In the end, this is exactly incentive compatibility constraint that is pinned down from the ordinary differential equation coming from the first order condition of the insurer, right? But this is a channel that is very important for the analysis, as you're gonna see, right? So let's start with the delta equals to 0, right? case. And then you're gonna see that the formula is very simple, because now you know the rho naught, right? So the equilibrium is gonna be unique, no dependence on the distribution, as you see from this formula, right? This is not new, this is in Rothschild sigma and also here, right? So the analysis for the two-dimensional case. So now let's suppose the delta is positive. Now you have really to play with this two dimension, right? So now for a given quantity, let's think about this, you know, this region of the equilibrium that we exactly have two types in terms of risk aversion that is choosing the same level of coverage, right? Rho L, rho H, and ML, MH, right? I know from the first order condition, these two types has to satisfy this condition here. And this implies that there is like the gap between the two types, low risk aversion, high risk aversion, that is choosing the same level of content. There is a gap between these two guys. So in a way, there is like, you know, for the same level of coverage, there is a, you know, a high risk associated to that low risk aversion compared to the high risk aversion, low risk, right? So this difference is positive, meaning that the low risk type is going to be higher than the high risk averse type associated to the same coverage. So maybe a picture is going to be more clarifying in terms of the characterization, right, of the equilibrium. So this is a numerical example from the uniform distribution case. So the equilibrium object is going to be like this. So if you see the, you know, for the high level of coverage, then you're going to have just one type choosing that level, which is going to be exactly the high risk averse type, right? So these guys are, you know, separating, right? These guys are going to be unique, right? As in the one-dimensional model. And the same for the low part, right? For the low part, you know, for the low coverage level, you're going to have only the low risk averse type choosing that level, just a unique type. But in the middle, you're going to have this phenomenon here, right? For a given level here in the middle, so you're going to have exactly two types. One each is the low risk averse, as I said before, this guy is going to be higher, right? For associated to the same level of coverage, and this guy which is low, which is the high risk, right? So these guys are pooling, and the average risk, you know, the average of these two types is going to give you the average price, right? So this is exactly the average risk. So I'm doing a convex combination given by this endogenous weight that comes from the equilibrium, right? That I was saying before, right? So that's pinned down. As you see, the price function is going to be exactly this black line, which is exactly the average risk for every possible risk level. You see there is a transition between these two regions, the separating and the discrete pooling region, which is going to be complemented by a continuous pooling. You see here these small intervals here of low and high risk averse types. These are exactly the pooling types, continuously pooling types in the transition. That's the way to make the price function a continuous function, which is a necessary condition to be an equilibrium in the first place, right? So these are the transitions. So we're gonna have this kind of 5-region situation: separation, continuous pooling here, discrete pooling here, continuous pooling again, and then separation again, right? And to give you a little bit of the idea, now, as I said, you know, I'm going to play with the delta, making the delta going to 0. What's gonna happen with this picture? What is gonna happen in this picture is that the discrete pooling part is going to be cover all the regions. So you're going to push this pooling upwards and this pooling downwards. So as if these two curves are going to be approximating this one-dimensional thing, right? So as you approximate the one-dimensional model, you're going to approximate with this discrete pooling region, right? And that is going to be important because this is going to be the transmission of the multidimensional aspect of the model, right? The one dimension to the multidimensional aspect of the model is through this discrete pooling region, which is the essential element of the equilibrium analysis, right? So this is the proposition, is just to say, you know, this is exactly the proposition that materialized the picture, right? I'm not going to go there, but there is just one important observation, is that for every fixed small delta, there exists not only one, but a multiple equilibria for this model. really have a one-dimensional parameter that maps all the possible equilibrium, like this one that I'm presenting in the picture right here. So there is no uniqueness in this kind of situation, right? So because of the multiplicity, what are you gonna do here? So you know,
sorry, Humberto, I missed in the picture. Where's the multiplicity?
You know, the multiplicity. You know, the multiplicity. You know, I don't have much time to explain that, but it comes with the fact that the place we are doing this pooling here, that gives you the transition between the separation and the pooling part. This is not completely determined. There is some indeterminacy that you can play with. So there is a small interval where you can play, where you start the transition from the separation to the discrete pooling. When you pin down that, everything else is going to be pinned down, downwards. That's the nature of the multiplicity, right?
So you have a continuum of possible intervals.
Yeah, it's a continuum of, you know, continuum ways to do this transition, right? It's not very big. There is like a limit to do that, but there is like a limit. And this comes some because that is going to impact. There is no way to really say that there is like a Pareto dominating equilibrium in this class, right? We thought about that, and it's not possible at all. So what are you going to do? So you're going to do the local analysis, right? So you come back to delta equals to 0. You know there is a unique equilibrium, no distribution effect, right? So in the equilibrium characteristics, just learn that there is a equilibrium multiplicity. All the equilibrium is going to have this 5-region structure. So what you're going to do is you're going to leverage the fact that we know the exact equilibrium at delta equals to 0 and play locally with that, right? How you do that? The traditional way, right? You play with the Taylor approximation. So we span the price as a function of this parameter delta with the risk aversion dispersion. So you can write down the price in terms of the level times the first order condition and the second order condition. As you're going to see, the level and the first order approximation, these terms are not going to depend on the distribution, but the second order term is going to depend on the distribution. And that is the channel that is going to explain the, how the distribution is going to affect the price and the equilibrium outcome, right? So you take the derivative. What is nice is that the derivative at delta equals to 0 exists. That is very, very, complicated to prove that, but you manage to prove that the derivative exists up to the second order. And these two terms, as I said, are not going to depend on the distribution, but this term, the key term, is going to depend on distribution. And with that, because all these terms are going to be uniquely pinned down, because of this uniqueness of these terms, then you can say sharply what is going to be the effect, right? So we play with the Taylor approximation, and since we have the uniqueness of this expression here, for any possible approximation, for any class of selection of equilibrium you're taking the selection, they are going to have the same approximation terms, right? So here is this key term that I said. So you see it's an ugly formula, but I want to really highlight the fact that here, exactly in this formula here, it shows up the hazard rate of the distribution of risk. And that's the channel, that's the important channel that is going to explain the, the impact of the distribution prices through the second order term, right? I'm running out of time, so let's go very briefly. Let me explore this formula to do two exercises. The first one is the signal disclosure, right? So what is a signal disclosure? What is a signal? So a signal is just a set of signal which can be potentially informative about risk, which can be disclosed, right? As our motivation, this is the kind of risk classification you can think as gender, age, or things like that, demographic characteristics that are going to be the signal. So the signal structure is just a function for each X, for each S in this set. This is going to give a distribution, the probability of some risk to show up, right? So that's the function that describes the probability of a given mu, given that you see a signal S, right? So I'm going to denote for each type in my model, mu and rho. U of mu and rho is going to represent the utility of the insurer. Since the insurance company has zero profit, the only action in terms of the welfare analysis is in terms of this function here, right? U of mu and rho. And when you have the signal disclosure and S is observed, you're going to denote U in superindex S to represent the utility given this exposed signal revelation, right? So this is the difference. We're going to omit the delta in the notation, not to be very, not to make it very heavy. And when you say that a signal disclosure is entering welfare improving, you say that the signal structure is going to be entering welfare improving if for any, and I want to write that, any distribution of type. So in a way, it's going to be robust to any possible distribution of type. And every possible realization of type, the expected utility in terms of the signal disclosure is going to be higher than the utility is going to achieve if you don't have signal disclosure. If you take, the X distribution, you don't consider the signal. So what I'm saying here is that I disclose the signal, so I see the realization in terms of the realization of the signal. I take the expectation of that, right, and see when this term here is going to be bigger or not to the benchmark case when I don't disclose. I take the average of the distribution in terms of the signal, right? So if this happens, I'm going to say that the signal structure is welfare enhancing. Do you understand the definition? Is it clear? All right. So I want to highlight this is a stronger notion than ex-ante criteria because I'm taking this type by type realization, right? So it's a notion that I'm considering type by type. So it's enhancing in terms of all types, all possible types in the economy, right? So let's fix ideas just to, how much time do I have? I'm out of time, right? Almost.
You can take like 4 more minutes since we started a little late.
Let me go very briefly here. So let's think about the binary case, which is simpler. So suppose that we have 2 signals, good and bad. Good, bad means that, bad means that, it's more likely that you're going to have like the bad signal as you go, as you increase the risk, right? So in terms of the monotonicity here, to fix idea, this pi function is going to be increasing, right? If S is B, and it's going to be decreasing if S is G, right? Which is the same that the ratio of these 2 densities is going to be, these 2 probabilities is going to be increasing, B over G, right? Which is the likelihood of these two signal in a way. So the proposition that we have here is a signal structure is entering welfare improving if and only if it's monotonic. Monotonic meaning that likelihood to be increasing. So I won't have time to go, it's a pity, but I won't have time to go really to the intuitive idea here. But the thing is that, if you see the effect through the statistical element, it's true that you have an equilibrium. So as you disclose, you're going to have the reaction of the agent. So they are going to re-optimize and choose different coverage. But let's fix, suppose that the only thing is a statistical effect. As you disclosure, so you disclose a good signal, it means that this is going to be good news about the types that are choosing higher risk, higher coverage level than you, because of the top-down effect that I showed in the formula before. And because of this channel, I can lax the incentive compatibility constraint when I disclose a monotonic signal, a signal that releases more information about high risk when the signal is bad and good risk when the signal is good, right? That's a little bit the logic behind this argument that I don't have time to go through. When you don't have a monotonic signal, you can show really with extreme examples that that the welfare analysis go in the other direction, at least for the very low risk types, right? So you show that for the low risk type, if you disclose a no monotonic signal, that can be harmful for low risk in the population, right? That's another point. And in terms of generalization, so monotonicity I present in the case of binary case, but you can generalize that with this notion of the Kullback-Leibler divergence measure, which exactly, it's a kind of metric, but it's not a metric indeed. It's a positive measure but it's not symmetric and does not satisfy the triangle inequality, but it just essentially says that if two measures are different, are divergent, they are more informative. And the monotonicity condition here is to say that if you take, like, let's say risk mu and mu prime, if mu prime is greater than mu, so it means this divergence measure is going to be increasing. It's going to be more informative as you go up in terms of the risk level, right? As you go up in terms of the risk coverage, another way to see that, right? So this is a generalization of the monotonicity condition of the binary case, and the results generalized to this very general structure of signal, right? In terms of the comparative statics, the thing, if you go back again to the formula I presented you before, the second order approximation, you're going to see that mechanically, now if you compare to risk distribution, the comparison in the end of the day is going to be given by the hazard rate comparison between these two distributions, family B and family A. So suppose that you increase the risk in terms of log likelihood, then it's mechanical that the price is going to go up, right? That's essentially the thing. So the results we have is that with MLRP, which is the stronger notion of comparison, you really have this negative effect on prices. High risk in terms of MLRP order is going to represent a negative effect on price. In terms of the distribution of risk aversion, if you increase the willingness to pay for insurance, which means that we increase the distribution towards high risk aversion, then you have a positive impact in terms of price. The price is going to go down, right? So briefly, the conclusion, I'm going out of time. So what we do in this model, in this paper, is we study welfare impact of risk classification. We translate that as this signal disclosure exercise. We present really attractive model with new distribution effects, which are not present in the one-dimensional models in the literature. And you do this novel exercise in terms of signal disclosure, showing that novel conditions characterize welfare improving signals when exactly we have welfare improving signal structure, when it's good or not to have release of information about some demographic characteristics of the agents. And in terms of the risk classification, we show that the MLRP is the right way to do the comparison between different families of risk distribution. That's it. Thank you very much.
I've got a question.
Yeah.
Umberto, I'm curious if you guys know anything about the monopolist case.
Well, the monopolist case, there are a lot of papers. The monopolist case, there is a paper by Shell and oh gosh, it's one-dimensional model. So the hardest thing is about two-dimensional model. It's really hard. Right, it's really hard to characterize multidimensional models, right? So this is the first thing. Really, me and Vitor and another co-author is really trying to push this analysis to the monopolistic case. So you're trying really to see how is going to be the comparison of this model here that I just present you in a real two-dimensional continuous type model. And in the goal of the paper is really to do one of the goal of the paper is really to do the comparison between the monopolistic and the competitive case. For the one-dimensional model, there are a lot of papers. There is this very recent paper in Theoretical Economic Journal. Shelley, do you know, Vitor, the authors is...
I mean the screening with two-dimensional property information?
No, the one-dimensional, the paper that showed up like a couple of years ago in Theoretical Economics.
The one-dimensional is going to be super standard, right?
It's super standard, but there are some interesting issues about exclusion, pooling.
Right.
There are some issues that are interesting in the insurance case, but there is, as far as I know, there is no such analysis for a model like this.
You said that you're working on the double continuum case.
Yeah.
But why not taking exactly the model you have, which is a continuum for risk and like a two type risk aversion structure?
Well, first
Wouldn't
we have
that
a hope.
help?
Yeah, first, you know, you really want to understand how this analysis that we do, like the local analysis, could be extendable to a real continuous two-dimensional model, right? If you have a hope to have some way to pin down, you know, uniquely the equilibrium, right, or to understand better. So if this two-dimensionality in terms of the being continuous in the two dimensions is going to put more discipline in terms of the characterization of the equilibrium, if this is true or not. So that's one of the goals, right, to really understand if you really play
relevant, and that's relevant already in the competitive case, right? Yes,
exactly. So the idea is exactly to do the comparison, the competitive and in the monopolistic case, in this project. Yes, Vitor.
And also, just to complement on the related digital monopoly screening, so the paper that Humberto mentioned is by Chade, Schle, where they solved the one-dimensional model in quite general sense in the monopoly. And there is a paper by Lafon, Masking, and Rocher, like an older paper, where they essentially solved the two-dimensional model that we're looking at here, quadratic model, but with private values. So it turns out that the presence of common values actually muddles things up quite a bit, even in the monopolist model. So that's still an open question.
Yeah, and we're working really with the call of one paper that tries to generalize this Rocher, Masking, Lafon, Rocher paper, which is Sergei Serenov, Vitor's colleague at UBC.
Very, very nice, guys.
Thank you. Sorry for the time.
This is very good discussion. But let's move on to Paulo's paper.
Yeah, let me stop.
Yeah, thank you.
Okay, let me share mine.
Sorry, Paula, for stealing a little bit of your time.
It's okay.
Okay, I'll make sure to keep you all here for as long as I need.
All right, take it away, Paula.
Let me put this full screen. Okay, so first of all, I wanted to say that I'm very happy to be here in Brazil, even if virtually. But okay, and I'm happy to present my paper, which changed a lot since I submitted it to the conference, and even the name has changed, okay? So I'm gonna present my paper, which is called Advisors with Hidden Motives. So, okay, let me start by remarking that there's many situations in which we seek information from sources that are conflicted. So just a few examples, we consult with financial advisors that many times receive commissions that are undisclosed, and they receive these commissions from the product providers. We also watch Instagram influencers exalt products that many times they are paid to review. And we even rely on academic research that is many times funded by pharmaceutical companies, okay? So just to look at one of these examples a little bit more in detail, let's say if I'm thinking about a financial broker, say I'm thinking about like Morgan Stanley, okay? They usually have these big equity research teams that are producing information and reports on like all the products that you can trade through them, okay? So many times you can see like a report on a stock that will say, we'll have like a compilation of a bunch of publicly available information on this stock, but also has a bunch of information that's produced by this team. So they have like forecasts and analysis that are produced by the team. And usually these reports also include like a recommendation to buy, sell, or keep this particular stock in your portfolio, okay? And there's many different empirical papers with a variety of empirical strategies that try to document that these brokers often will hide bad news about some companies that they're financially interested in, or that they are more likely to recommend products that they have high commissions on. And just in general, that these financial brokers try to steer consumers to make purchases that are more profitable to themselves. Okay, so they use their, I don't know, the disclosures of information to steer these consumers towards whatever they prefer. And this is a big regulatory concern. There's a lot of like in different countries, different policies of how to I don't know, address this. So like in some countries, financial advisors are required to disclose all the commissions they receive from product providers. In some other places, there are caps on how much or on what commissions you can accept and so on. So just to say that this is a big issue of contention, okay? So what I do in my paper is I propose a model with advisors that have hidden motives, okay? So in my model, I'm gonna have a sender who is the advisor who acquires information about a certain object, and he commits to some rule to disclose this information to a receiver. And this receiver can then see this information that was disclosed and purchase this object that he received information about, okay? And importantly, what is hidden about the advisor's motives here is that the sale of this object might be more or less profitable to the advisor, okay? And this object's profitability is not observed by the receiver, okay? So what I'm gonna do in the paper is study how the sender's hidden motives affect their decision to acquire information about this object and to disclose this information to the receiver, okay? And
can I ask a question? Yeah. Does the receiver see anything about the information acquisition by the sender?
I mean, they're going to understand what was the signal that was acquired by the sender.
They will observe. I mean, I know they won't observe they won't get to see the information, but will they know whether they are acquiring, let's say, more or less information?
Yes.
Okay. Not just as an equal. Okay, maybe it's too early. Okay.
Well,
sorry.
I'll get to that whenever we get to the model. But yeah. In any case, but my main result here that I'm going to show today is I'm going to characterize what the optimal disclosure rules for the sender look like. Okay. So in particular, I'm going to show to you that an advisor is going to optimally disclose some information about the object. In particular, he's going to choose to reveal good news about an object's quality whenever the object sale is sufficiently profitable to the sender. And of course, he's going to do that in order to increase the probability that this object is sold because he's interested in that. And on the other hand, he's going to also reveal bad news sometimes. And in particular, he's going to reveal bad news whenever the object's sale is not very profitable, okay? And even though there's not going to be anything in my model that's going to be explicitly called reputation, you can interpret this, that the sender is going to sometimes reveal bad news to create some reputation with the receiver, okay? So that the receiver knows how to interpret when the sender chooses, for instance, not to disclose any information, okay? So the sender is going to be managing his reputation with the receiver, so it's sometimes useful to reveal some bad news. And we're going to spend most of our time trying to look just like, given that we have some information already, how do we disclose this? But then I'm going to take a next step to show what are the incentives to actually acquire information. And I'm going to show you in particular that the sender's hidden motives can actually be an additional incentive to invest in acquiring information about this object, okay? And in particular, we're gonna see that this means that the sender's hidden motives may actually be beneficial to the receiver in terms of the overall informativeness that they get from this advisor, okay? In the paper, I actually say what implications, I tell you about some implications of this about policy, but I don't have anything of that sense here in my presentation today. So let me just make a small remarks on the literature here. There's a huge literature on information design these days, but I just wanted to remark that what I'm going to show you today, my model is related to these Bayesian persuasion models in the sense that I'm going to have this commitment that the sender is going to pre-commit to the way that they disclose the information to the receiver, okay? But my model is also related to this voluntary disclosure models, especially DIE in 1985, in the sense that the information that the choices the sender is going to be making is between fully revealing the information, so disclosing the information to the receiver, or not disclosing. Okay, so it's not going to be a information design problem per se, more like a disclosure model. Okay, so if you have any questions, I'm happy to take them. Otherwise,
so this is going to be a static model, so there is no dynamic interaction here. So So when you say reputation, is just, you know, interpretation of the fact you just described how the information is going to be released, right?
Exactly. So there is not going to be any dynamic here and no actual reputation building. But, you know, there are actually these new papers to some people here at NYU, like Ennio Sacchetti and David Pierce and Laurent Matevet. They have this new paper trying
I heard of. Yeah.
They're trying to justify that the commitment assumption in these Bayesian persuasion models can actually be interpreted as a repeated interaction.
That's exactly what I was thinking about. Yes, exactly.
So in that sense, you can think that there's like this flavor or dynamics in my model through this like commitment assumption. But of course, I don't actually explicitly model the reputation building here. Although I do have some things to say about it. I'm happy to talk about it at some point.
Great.
Okay, let me tell you what my model is. So as I said, I'm gonna have a sender who is going to inform a receiver about some object, okay? And importantly, this object is gonna have two characteristics. So the object has a quality, which I'm calling X here between 0 and 1, and it's drawn from some common prior. And this object also has a profitability, which I'm calling W, which is drawn from some other common prior that I'm calling W here, big W for the little w. And this quality and profitability are gonna be independently drawn. Moreover,
could be positive correlated. The result would stand in is natural, more a natural case. So you would think that higher quality is gonna give you more profitability, right?
So let me tell you. So whenever I'm talking about my optimal disclosure rule, this independence assumption is not important. So you could just like, I'm stating this as independent, but the proposition is true for whatever distribution, okay, the proposition that I'm gonna show you. But whenever we're talking about actually the incentives to acquire information, it is important whether these things are positively correlated or not. And in whatever I'm gonna tell you today, I'm gonna take them to be independent.
All right.
Okay. Okay, so moreover, this receiver is going to have access to some outside option, which I'm calling Y, which is also distributed. It's also between 0 and 1, and it's drawn from some common prior, big Y. So I'm still going to tell you more information about like who sees what and what information they have at some point. But the end goal is that this receiver is going to have to choose one of two actions. So the receiver has a binary action to take, which I'm going to be calling buy or not buy here. Okay. So if the receiver does buy the object, they're going to receive exactly the quality of the object, X, okay? And in that case, the sender receives the profitability. So what this quality and profitability are saying is that quality is what matters to the receiver and the profitability is what matters to the sender, okay? And that's what they receive upon the sale of the object. And on the other hand, the receiver may choose to not buy this object, and in that case, they keep their outside option, which is Y, and the sender gets 0 because no sale was executed, okay? So let me just read this in terms of the financial advisor case that I was telling you about. So you can think in the context of the financial advisor, you should think this about the quality as the suitability of this project, of this asset to the investor, and the profitability could be whatever commissions the sender is receiving from the financial product provider, okay? And importantly,
so the commission is kind of uncorrelated with the quality.
Right, here I'm taking it to be uncorrelated, but again, it's what I said to Umberto. For the first result that I'm going to show you, you could think of it whichever way you want. Okay, so I'm telling you about buy or not buy the object, but I'm not mentioning any price. So in particular here, when we're thinking about this context of the financial advisor, many times the prices of these assets are not really negotiated between the financial advisor and the investor, right? But rather, they are already some price that is set by the market. So I'm taking here the price to be some exogenous value that was set by the market. And so you should interpret this quality X as already being the quality of this product net of the whatever price it costs, okay?
You can think of this as like a brokerage firm that it has like the advisor tells you buy this stock here, and then he gets a commission, and the stock has some quality that he has information about, and he discloses some information to you as a buyer.
It's exactly that. okay? So, and in particular, this one, just one more thing that I wanted to talk about. So when we think about this distribution of receiver outside options, what you should think about is that, so let's say that I'm creating like this report from Morgan Stanley. Many people are going to observe this report, okay? And they're going to, and each of these people, they have like, I don't know, different preferences for risk or different, I don't know, outside options, things that they are already invested in. And you should think of this distribution big Y as the understanding of the sender of what the distribution of like these people's private investments are, okay? So they understand like on average how people are, I don't know, whatever they are already invested in, and how they would react to whatever information they receive. Okay, so now let me tell you a bit more about actually how the information transmission happens here. So we're going to, I told you that the sender is going to acquire and then disclose information, but first we're going to just pretend that the information has already been acquired. Okay, so let's say that the sender has access to some signal of this object's quality, okay? So it could be that he observes perfectly what the object's quality is, but it could also be that he just observes any signal, okay? So whenever there's a certain realization of the signal, the sender understands what that means in terms of what the expected value of the object's quality is, okay? So, and in my model here, like the receiver is risk neutral. So all that's gonna matter to him is actually the expected value of the object's quality upon the realization of the signal, okay? So in that case, we can understand, we can just like describe the signal that the sender has access to as just a distribution of posterior means that is induced by this signal, okay? And I'm calling this distribution S for signal. Okay, so the sender has access to this technology, but before either the quality or the profitability or the signal realization are drawn, the sender pre-commits to a disclosure rule of how he would go about disclosing these signal realizations to the receiver, okay? So precisely what he's gonna do is that he can choose for each possible signal realization, he can choose whether the signal realization is disclosed to the receiver or not disclosed to the receiver, okay? And importantly here, the sender can make this decision conditional on what the profitability of the object is. So specifically, for each profitability W and for each signal realization X hat, the sender is going to choose a disclosure probability of this realization, okay? So a disclosure policy here is just going to be exactly this function that maps profitabilities and signal realizations into a probability of disclosure, okay? And
just to clarify, the commitment is made prior to the sender getting to know the profitability. So there's no informed principle problem.
Right. So I'm not like competing with another one. Yeah, so I don't know yet, but I can condition on what it's going to be tomorrow, my profitability. Yeah, okay.
Paula, quick question. Yes. So just related to the motivation for commitment with respect to reputation. So if I'm thinking of the investment decision, I can see how over time I would understand how informative the signal is about X because I see if the investment's paid off or not. But if the signal is also informative about profitability for the sender, how would I learn? I would have to be observing over time which commission the sender obtained. Like how would I end up learning how informative it is about W?
Right. Well, I guess here what's going to happen in my model is that to the receiver, it doesn't matter what the profitability is. So he only cares about what this X is. Okay. So to some extent, I don't know, he doesn't even want to learn about the W. Okay. So that's just a moot point a little bit. But I can also, I prefer to talk about this later, but like I can also argue with you that actually the commitment with respect to the W dimension is not actually going to be important. Okay, so if I could in some way just describe a partial commitment where I'm committing on the X dimension, but not committing on the W dimension, then that's going to be sufficient. Like it's just not, that part is not important here. And it's not important precisely because the receiver doesn't care about the W. Okay?
Oh, great, thank you.
Okay.
So in terms of sort of the Bayesian persuasion literature, so So should I think of this as kind of placing a restriction on the experiments that you design, or because because in
you
a sense, yeah, I'm just trying to understand, because in a sense, a typical Bayesian persuasion model, in a sense, is going to allow a greater degree of freedom. Is this the right way to think about this?
Yeah, so you can think about it that way. So it's just, I'm telling you a class of signals that he can pick from, which is a subclass of whatever is allowed in Bayesian persuasion, okay? And but I will argue that it's not just like a restriction in terms of like, oh, I can't solve this, so I'm going to solve this, but rather it's just a completely different interpretation. So it's just like, it's as if we have hard evidence. So it's like I produced whatever the forecast is about this product, and I can choose to tell you that or not tell you that. Okay, so while in Bayesian persuasion you could think that it's like more of a problem of I'm designing classes, so I could tell you this is an A product or a B product or so on. Okay, so I feel like in reality there's both of these things. I feel like the Bayesian persuasion thing happens more often in the context of like credit rating agencies, while something like what I'm telling you is more, I don't know, commonly observed in this context of like financial advisors, for example. Okay.
And just sort of just a quick follow up. So, but in a sense, so by sort of making this ex ante commitment, sort of you're killing this the signaling dimension. No, that in a sense that your decision whether to reveal some information or not in itself might have some information on content. No?
Right.
So, and have you thought about this, or I don't know. Anyway, just maybe this is taking you too far away from what the paper is, but I'm just interested in it.
No, okay. So these models where like we do the cheap talk version of a disclosure model, they exist out there. And like, for instance, this model that I mentioned to you in my literature, the DIE model, that's pretty much where it started. Okay. Again, I want to argue, like I told you to Humberto, that like one way we can think about these like Bayesian persuasion thing is that we can somehow create like a reputation. So in that sense, it's just like, it's like almost taking into account like I don't know, a dynamic version of this type of models. Okay, so it's just, I mean, it's that question exists and it's out there. The papers exist. Okay, so let me tell you. So this is, as I told you, what the disclosure rules look like. Now let me tell you from the perspective of the receiver. So let's say that there's a certain realization that the sender chose to disclose to the receiver. Then what that means is that the receiver is going to have his mean posterior be exactly equal to x hat, which was the realization to start with. And however, let's say that if the realization happened and the sender chose not to disclose this realization to the receiver, then how does the receiver create his mean posterior in his head? It's like this. So he takes the average quality amongst all the possible situations in which the sender would not have disclosed the signal. Okay, so and then calling that average the XND, so the X of known disclosure. Okay, and okay, so and in particular, it's important here that because the receiver does not observe the profitability, he is conflating here in this expectation situations in which the object was very profitable and the sender didn't reveal, with situations that the object was not very profitable and the sender didn't reveal. Okay, so this through this pool here that the sender can create is where he has some ability to manage the expectations of the receiver. Okay. So let me just say exactly what the timing is. So first of all, the sender is going to commit to this disclosure rule D. Next, the nature is going to draw the quality and the profitability of this object, and the disclosed signal is going to be realized according to the disclosure rule that the sender picked. And finally, the receiver is going to draw his outside option Y, and he's going to choose whether to buy this object or not buy this object. In particular, he's going to buy this object whenever his posterior mean is higher than his outside option. Okay, so yeah, and then payoffs are going to be realized as according to what I said.
So just to clarify, the S is exogenously determined here, right? You're not going to be choosing this.
So for now,
distribution
I'm
of signal.
taking this S as given.
Okay.
Okay. Okay. So Okay, so let me tell you a little bit about what the sender's objective is here. So let's clarify what the sender's objective is. So let's look first down here. So suppose that the sender picked a disclosure rule, okay? So what this P of WD is what is the probability that the object of profitability W is sold whenever the sender picked the disclosure rule D, okay? So let me describe to you what that is. So there's two things that can happen. So let's say that a signal realization X happened, and then he can either disclose that signal realization, which happens with probability D of WX, okay? And in that case, the receiver perfectly understands that the signal was X, and he buys the object with probability Y of X, okay? Where this big Y, remember, is the CDF of the receiver's outside option. So the probability that the receiver's outside option is lower than this X is Y of X, okay? Okay, or on the other hand, it might be that the sender chose not to reveal this, not to disclose this realization to the receiver. That happens with probability 1 minus D. And in that case, what the receiver does is he thinks that the quality of this object is X and D, so the X of non-disclosure, and so he buys whenever his outside option is less than X and D. And of course, this X and D, the disclosure rule is inside there. Okay, so this is an endogenous object itself. Okay, so let's say that I chose this disclosure rule, and it implies a bunch of these probabilities of sales for each different profitabilities. Okay, so what is the value to the sender? The value to the sender is exactly the expected value of the product between the profitability and the probability that the object is sold given its profitability, okay? So you see here, that's exactly what I have here. So W times the P of W, the expected value of that, okay? And importantly, I can just split this into two terms, okay? So I'm gonna split this into one term, which is gonna be the expected profitability of this object times the expected probability of sale, plus a covariance term, okay? So on the one hand, what the sender wants to do is he wants to maximize overall the probability that this object gets sold, okay? Any object, whichever the profitability is. And on the other hand, what he wants to do is he wants to maximize what's the covariance between the profitability of the object and the probability that the object gets sold, okay? So I guess this is a pretty clean way to think about this, that the sender has this conflicting, sometimes you're going to see that it's conflicting objective of maximizing both the overall probability of sale, but also the covariance. So sometimes I might be willing to give up on the overall probability of sale if that means to maximize the covariance, okay? Okay, so
Paula,
that's
just a quick question. So this expression of P seems to say that whenever I disclose, the agent buys, right? Yeah. So I'm never going to disclose a signal that leads to the agent not buying. Is that the case?
Right, but I pre-committed. So I'm also affecting the XND itself with my disclosure rule. So I might want to disclose to you some things that are negative if that means that it would improve your overall perception whenever I choose to not disclose. Okay. So, okay, so now let me tell you what my optimal disclosure rules look like. So here's my main proposition. So the optimal disclosure rule is going to have a threshold structure. So in particular, there's going to be a quality threshold, which is going to be a certain number, X bar, and there's going to be a profitability threshold, W bar, and it's going to be such that the sender is going to choose to disclose a realization whenever either both the quality and the profitability are above the threshold, or both the quality and the profitability are below the threshold, and not disclose otherwise. So one way to think about this is that whenever the quality and the profitability are above the threshold, for instance, it's a situation in which the quality, which matters to the receiver, and the profitability, which matters to the sender, are in agreement. Okay, so it's like I disclose whenever both the quality component and the profitability component agree. So they're either both high or both low. And I don't disclose whenever they disagree, okay? And in particular, you can see here that while the quality threshold is just a number, the profitability threshold is actually a function, okay? So this W bar depends on what the X is. Sorry, I should have been more clear. I'm plotting here the quality on the X-axis and the profitability on the Y-axis, okay? And I did my best here to try to draw a quality, to try to draw a profitability threshold that looks pretty silly, okay? So just to let you know that in this proposition, I don't yet have any characterizations of what this threshold looks like, okay? So, but I do, once we put in some assumptions on what the distribution of outside options is, or distribution of signals or so on, I can tell you much more about the characterization of what this function looks like. But so far, let's just take it for what it is.
So how important is for this result is the assumption that the X and the W are independently distributed?
So not important at all. So
okay.
You might as well just think that it's any distribution. Okay.
Okay.
So, but this threshold curve could be very, very weird, right? In principle, it's like could jump, could do.
So for instance, let's say that we assume that the distribution of the receiver outside option is continuous. That is already going to imply that this is going to be a continuous function. So it's not going to be too crazy. Okay, so like with mild like assumptions, I can get that this function is going to be somewhat reasonable. Okay, but okay, but just the way that I want to, yeah. So the way that I'm writing this proposition right now is just saying that to the extent that these things are quadrants, I reveal on the first and third quadrant, and I conceal on the second and fourth. Okay, so I'm going to try to give you a proof of this. So let's look. So let's say I take any disclosure rule. So I'm just trying to plot one here that is, I don't know, silly. So let's say that here in red is every situation in which I choose not to disclose, and in white is every situation in which I choose to disclose. Okay. So let's take as given this disclosure rule. So knowing what the disclosure rule, I can use it to compute what that X of non-disclosure is. So what I can do is I can just compute what is the average quality amongst all the situations in which the sender chooses not to disclose this signal. So what is the average quality amongst all the red situations here? So I can always do that. So suppose that it falls right here. Okay, so okay, now I'm going to try to argue to you that this disclosure rule that I drew here can be improved upon, okay, in a particular way. Okay, so look, let's take first a certain realization, X hat, that happens to be below the X and D, okay? So if I take the situation here, you see that, well, in this particular disclosure rule that I drew, I am not disclosing for low values of the profitability. I am disclosing for high values of the profitability. But because this X hat is below X and D, I'm better off whenever I get the known disclosure, right? So you see that like upon known disclosure, the receiver would think that the quality is X and D and would buy it with probability Y of X and D. And upon disclosure, he would think that the quality is X hat and would buy it with probability Y of X hat, which is smaller than Y of X and D, okay? So in this case, I could maintain the expected probability of sale, but increase the covariance between profitability and probability of sale by flipping this, okay? So what I did here is to the receiver, it doesn't matter whether I am he doesn't care about the profitability. So to him, it doesn't matter whether I am hiding when the profitability is low or whether I'm hiding when the profitability is high. So if I maintain the probability that I am disclosing given the X hat and I just flip it, to the receiver, that makes no difference. But to the sender, that is very good because it improved the covariance between the profitability and the sale probability, okay? And sort of I can do the opposite here if I take an X hat that is above the X and D. So in this case,
with correlation, this is not true, right? This mechanism is not true.
It's still true. So for instance, here I didn't tell you anything right here about what the distribution is. So for instance, let's say I take the marginal. So let's say that I tell you that I'm going to reveal to you when the signal is 0.2, I don't know, half the time. Half the time when the signal is 0.2, I'm going to reveal it to you. Okay. So let's say that is correlated. So let's say that, yeah, what I'm saying is like, I can just reveal the highest ones. I mean, I can conceal the highest ones that are going to happen for the 0.2 here or whatever. Okay, so let me try to be more clear. So this X hat here, it doesn't matter that like the distribution is the same for any, I don't know, for any profitability. So you just take any distribution. I can always flip it this way.
I guess the reason is because I don't care about W. No,
yes,
buyer,
no,
yeah,
I see.
Yeah,
you can do any relabeling you want, just keeping the same probability in the end. That's going to be the same.
Right. So if I commit to a marginal, that's all the receiver cares about. And then how these things are correlated, he doesn't care about. Okay. So I can just pick that one to my advantage. Okay. So as I said, I can flip it this way. And then whenever I take this X hat that is actually higher than the X and D, in that case, I'm happier if I have if the signal gets disclosed, and sadder if the signal gets concealed. So what I do is, again, I flip it. So I reveal it for the high profitability guy, and I conceal it for the low profitability guy. And that part was already the correct way up. So anyway, so and there you have it. This is already has that structure that I told you. There is some threshold W, which can be described by some function, and some threshold X hat, which happens to be exactly equal to that X and D that I told you. Okay, so I have this threshold structure whereby I reveal on the first and third quadrant and conceal otherwise. Okay.
So do we know whether this W upper bar is strictly between W upper bar, the strictly interior in the set of W's? I'm just thinking whether this can reduce to just the usual, I reveal when it's sufficiently high, when X sufficiently high, and don't reveal when X sufficiently low.
Right now I drew it. Well, I told you that the W was just in the real number, so I made it not bounded. So I mean, it's always interior. I don't know, it has to be, but I can tell you more. So for instance, let's say that there are just two profitability levels. So it could be like low or high or something like that. It's always going to be between the low and the high. Okay, so at least somewhere this function is going to be between these two things. Okay, so just because I'm having fun, let me tell you a bit of like a further characterization that I can have. So for instance, I can tell you that whenever the distribution of the receiver outside options is uniform. Okay, so let's say in that case the y is a linear function. I can actually tell you that this W threshold is also just going to be a number. Okay, and it's also going to be equal to the average profitability amongst all the non-disclosed signals. And if, for instance, the distribution of the receiver outside options is convex, I can show you that it's going to be a decreasing function, which is going to exactly cross this W and D at X and D, and the opposite if it's concave. So it's going to be a increasing function. So
you have closed form solutions for that? So
I don't have closed form solutions, but I have an algorithm. So if you tell me, you see that here for each, if I take two numbers, so let's say I have a candidate X and D and a candidate W and D, then I can tell you exactly what this. Then I have given an X and D and a W and D, I know what the closed form solution for this function is. So basically, I can just write an algorithm that's going to test out a bunch of combinations of XND and WND, and I can just tell you exactly what's going to be the optimal disclosure rule. Okay, so it's pretty general. I can always find it sort of easily in my computer. Okay, so I have intuitions and lots of things to say about the convex case, the concave case, but I feel like I'm just not going to have time to get there today. So let me just leave it at that. Okay, so importantly, one way that we can look at this is that let's say I take a very high profitability object. Okay, then we're gonna have this characteristic that I'm gonna like conceal bad realizations and reveal good realizations. And likewise, if I take a very low profitability object, I do the opposite. So I reveal bad realizations and I conceal good realizations. Where of course, if I'm like somewhere in the middle, I could have like some I don't know, some alternating revealing and concealing of the realizations. But I just wanted to show you another picture. So another way to look at this is by plotting what is the posterior mean that is induced on the receiver for each possible signal realization. Okay, so what I have here is on the y-axis is the receiver posterior mean, and on the x-axis is the signal realization. And on the left, I have the case of the low profitability object. So you should think about a very low profitability object. And on the right side, I have the very high profitability object. Okay, so what's happening here is that if I'm a very low profitability object and I get a bad signal realization, it gets realized and the receiver exactly understands what the posterior mean is. So I have the 45-degree line. Versus whenever I have a high profitability realization, I don't reveal that to the receiver and he thinks that the quality is X and D, so that's just a flat. And on the other hand, for the high profitability object, it's the opposite. So for the low, I think it's X and D, and for the high, it's the 45-degree line. So the way that I like to say this is that what the sender induces on the receiver is that he makes the receiver think that the low profitability object is at most X and D good. And he makes the receiver think that the high profitability object is at least X and D good, okay? And you can see that by doing this, what the sender is doing is he's effectively steering sales that are going from the low profitability objects to the high profitability objects. Okay, so just making you buy the thing that I like better. Okay.
Yeah, just wanted to mention that, you have only one more minute, so just bear that in mind.
Okay.
I mean, you can take 2.
Oh, I thought it was like 15 more minutes. I thought it's crazy. Okay. Okay. So let me, I was going to tell you, okay, I'm going to tell you about information acquisition, but I'll tell you a very silly case. So let's say that the acquiring information is costly to the sender. So in particular, let's just say that instead of committing to just the disclosure rule, he actually first chooses also to acquire or not acquire the signal of the object's quality. So either I have no information or I have a signal, okay? And having a signal costs K, okay? And what I want to do is I want to relate the degree to which the sender has hidden motives with his decision to invest in this information to start with. So here I'm just defining what like more hidden is. So I'm going to say that the sender has transparent motives if the distribution of profitabilities is just a degenerate distribution. So in that case, the receiver just understands fully what the profitability is. And in particular, I'm going to say that he's more hidden if he has a mean preserving spread of the distribution of profitabilities. Okay, so if my distribution of profitabilities is more spread out, I understand less, the receiver understands less what the motivation of the sender is. Okay, and the proposition that I wanted to show you is just to say that here in this case, the sender is going to acquire this costly signal of the object if and only if his motives are sufficiently hidden. So if a sender is acquiring the signal and I make him more hidden, he continues acquiring the signal. And on the other hand, if he's not acquiring the signal and I make him less hidden, he still does not acquire the signal. Okay, so there's this monotonicity. So if I am sufficiently hidden, I'm going to acquire the signal. And just let me tell you one thing, because it's just in one line we can see this. So if I look again at this objective of the sender, his revenue, So he wanted to maximize both this expected value here as well as the covariance. But you can see that if he has transparent motives and his distribution of W is a degenerate distribution, then this covariance is trivially equal to 0. Okay. So what that means is that, for instance, if I have transparent motives, all I can do is try to maximize this expected value here. So it's like I can use this information in less ways. Okay. So versus if I have hidden motives, I can sort of like use it. I have more scope of what to do with this information in my benefit. Okay. And so if I am sufficiently hidden, I do acquire this information, and I do end up being more informative to the receiver as well. Okay. But just because trivially in this case, in the case that I didn't acquire the information, I couldn't be informative at all. In the paper, I have more, I don't know, general results about like how to acquire the cost of information and so on. Let me finish with one sentence. So what I want to say is that the takeaway is that the hidden motives of the sender may actually be here an additional incentive for him to acquire some information that is relevant not to himself, but to the receiver. So this hidden motives may actually be a way in which the incentives of the sender and the receiver are actually aligned. So they both get more out of this. And leave it there.
Very cool.
Is it always better for the receiver to face someone with hidden motives, or is it that it can be better? What's the result?
I said here maybe better. So I guess I can tell you more in particular cases. So for instance, if the distribution of receiver outside options is uniform, I know that it will be better.
Very nice.
I had one quick question, maybe, because I saw that, so in the paper you had this one-dimensional choice of information, right? There's one dimension that controls information, but I was thinking of an alternative that is more along the lines of what Braz asked. If you allowed people to acquire any information structure and you had a cost that is, say, monotone in the Blackwell order, right? So more informative signals cost more. Then you would just never acquire a signal that you would not want to reveal later, right? Like, so, you know, if you would,
So here, one important thing is that when I'm talking, of course, I should have told people more about like the setup of the acquiring that I have in the paper. But so here, when I say that these things are independent, when I invest in acquiring a signal about the quality, I'm investing in acquiring a signal about the quality for all the profitabilities. Okay, so it's like I'm gonna know, regardless of what this profitability is, what the distribution of signals are. So I might want to acquire some information that I'm not gonna reveal because I acquire it as a bundle for all these profitability objects. Okay, so it's like and then I can just selectively disclose whenever it's convenient for me. But if I could already invest in acquiring this thing as a correlated signal about the profitability of the signal, then I agree that there would be no reason to actually acquire things I am not going to end up disclosing. And those papers are also out there. So.
Okay, cool. All right.
Very nice.
All right, great. I think that's it. We can stop here. This is very good.
Okay. Thanks a lot.
Thank you.
Thank you very much.
Thank you very much.
Thank you, Eduardo, Braz, Rafael.
Very nice.
Nikki.
Thank you.
All the audience.
Bye-bye.
Thank you.
Bye, Vitor. Go have breakfast.
Or sleep again.
Yes. Back to bed.
Bye-bye.
Take care. Bye.